Isn't it wonderful to be here? It's a great place. Yeah. I'm amazed over the years that they let us come here among the professionals and do what we do. It's just been fun doing this. I joined this group in 1993. I had the privilege of watching the GBTV. This morning, Bob Kroll and I are going to talk to you about some of the things we're doing at Moorehead State University. And so you can see our 21-meter dish, our control room, and then of course we have mixed in here some of the Goldstone and DSN stuff because that's the nature of our talk. My paper, which unfortunately I did not get into the journal and I apologize for, perhaps it could be submitted for printing in the SARA journal at some other time, was titled this, because this is where we began from. Okay, these are some of the things you say, well, what does this have to do with radio astronomy? I'm going to talk to you about some of the technologies involved here, and incidentally, some of the missions that we're supporting that involve things we're interested in. We're in Moorehead, which is a relatively quiet place in the middle of nowhere, and my boss likes this picture, you know, because it kind of shows the bucolic setting. Of course, if you want a good meal, you have to drive an hour to get it. And this is our baby here. This was built back in the early aughts, and the purpose of this was a ground station and a radio telescope. So we actually began the whole program at Moorehead back in the 90s. I assisted. I was not on the staff then. I joined in 2005. But it began as a radio astronomy program. He wanted to do astrophysics. And then as he grew up, he decided that he really wanted to do some other things as well. And so, just like Senator Everett Dirksen said, $1 million here, $1 million there, pretty soon it adds up to real money. Well, over the time, he was able to get enough money to build this guy and get it put in. It was built by the same folks that built the GBT, Vertex RSI. Ultimately, we're at a university, and so our product is students. That's what we produce. We produce students, and students need jobs. So what we do gives them experience in areas that they're able to go out and get meaningful jobs in. We began in 2005 doing CubeSats, and that's a long and interesting story in itself. And my boss, when he began, Ben Malfris, when he began back in the 1990 time frame, all he had was an undergraduate program. He had no grad students. Well, those of you who are in academia or have degrees know that only grad students really do the fun stuff. Undergrads at most places don't get an opportunity to do anything really interesting. Well, I like to use the ancient Chinese proverb, man who does not have dog must hunt with cat. Ben did not have grad students, so he used undergrad students and he created an undergrad research program that gave them the opportunity to participate in real things, get their name on refereed papers, go to conferences and present material, and this began producing a quality of student that was pretty good. I was impressed when I began coming down from the Baltimore-Worcester area in the mid-90s and working with these guys. And so we see that they have this undergraduate research experience, which is very meaningful. They get a lot of hands-on instrumentation work. They get to do things. They get to build things, design and fabricate stuff. Of course, we still maintain the observational astrophysics program, but I have to tell you, we got two astrophysics guys on staff, PhDs, they're great guys, I love them. They're a little lazy. They don't really use the instrument like they should. And they miss a lot of opportunities, and so time has overtaken them because now we've gotten involved in ground ops for satellite systems and for space probes, and that's taking time on it. I also teach the senior thesis and master's thesis program. So they get project management experience through those as well as through the work that we do. I teach in the grad school, I do remote sensing, I do space communications, I teach in the undergrad, I did a microwave course there I designed, and I have a satellite comm course. Now I'm teaching a basic AC/DC course because I was unhappy with what we had. And we've also, Bob and I created a course for the freshmen coming in the door, who unlike us, in many ways, who had this experience of hands-on, building things since we were kids, tinkering with stuff, our dads did things, whatever. A lot of kids come into us and they want to do things, they don't have these experiences, which is why it's refreshing to see the young people who've been in the crowd with us, the young fellow yesterday with the interferometer, the young lady today, who are actually doing things, are getting invaluable experience because hands-on is what's lacking in the country today. We don't have enough people to maintain the ascendant position of the United States. The engineering and science, we just don't have enough of them. Don't have enough of these people. Then, of course, systems level engineering experience. We call ourselves a systems engineering house. We know a lot of things and a little bit about each of those things, and on a few things we know a lot about that topic. So we do a little about a lot and a lot about a little. These are some of the things that we've done. These are some of the satellites, CXBN-2 and 3. 2 has gone up and 3 is in the works. These are cosmic X-ray background nanosats. They're looking for the remnants of the Big Bang in the X-ray spectrum. We've used medical imaging technology, X-ray sensors in there. The latest ones, they're very successful. We're happy with them. And you say, well, hasn't somebody else done this? Yes. But it turns out that the big boys who've done this, they've got 2 sets of results. We're hoping to be the tiebreaker. So we keep refining our designs and relaunching this. So the Army decided back in the 2010, 2012 time frame to get back into space after 50 years. We were part of that effort. The Army got involved in CubeSats, and so we built this. This is one of the highest power CubeSats ever built. That array produces 85 watts. If you know anything about CubeSats, it's hard to get power on them. And then, of course, we've developed a standard 3U bus we use for everything. And we've had lots of little things along the way, but the guy at the top is the most exciting one. That's Lunar Ice Cube. That's going to be launched on the largest rocket to ever leave the surface of the Earth around 2020. It's going to go on STS-1, Space Transportation System, on what they call, well, it was Experimental Mission now. Experimental Mission 1, I forget what they call it now. But it's EM1, and it's going to carry the satellite to the moon. That's a 6U CubeSat. And it is involved in the search for lunar water. This is our 3rd engagement in the search for lunar water. We're intimately involved in man's return to space as we enter the 2nd space age for man. There's an awful lot going on that never makes it into the news because they're too busy talking about Trump's tweets. But we've decided to explore the solar system by CubeSats and robotic vehicles. And there's a whole lot of this going on, and I've become privy to it because we're involved with JPL and we get to see a lot of things. That particular instrument will have an infrared spectrometer on it, and it'll be looking for water in the mid-latitude regions on the moon. We've already discovered water on the moon. We know it's in the craters at the poles. That's a done deal. But it turns out the moon has an atmosphere. You say, what? Yes, during the daytime when the sun's beating on the moon, there's water molecules that actually move around, of course. At night they condense down and disappear, so it's very thin and tenuous. But I wouldn't have believed this, as somebody told me, there's actually water molecule migration on the moon. So people want to see where it's going so they can understand these mechanisms, because it costs about $10,000 a pound to put something in orbit. So if you take a gallon of water at 8.3 pounds, that's 80,000 bucks. If you don't have to haul water to the moon, you're way ahead of the game. You can haul a lot of other stuff like food and tools and supplies. And so this idea of searching for water on the moon has become such a big deal, as it is a stepping stone to the rest of the solar system. Okay, so that guy we're building currently, that's a 6U bus. You can see the big solar panels, and you'll get to see a little bit more about it. But we're involved with NASA Goddard Space Flight Center, NASA Marshall Space Flight Center, JPL, of course, this company Busek. This has electric propulsion on it. It has iodine electric propulsion system, an iodine ion thruster engine, which is kind of cool. It's pretty new technology. And we're working with this company Busek up in Natick, Mass. They are the world's premier ion propulsion system company. You've probably never heard of them because they're on a lot of spook satellite stuff where they have these huge thrusters that move spook satellites around. But we got to meet the guys and work with them, and they're really a lot of fun. Some of the other things we've done, we have Bob Twiggs on staff. For those of you who might not know who Bob Twiggs is, he's the guy co-invented the CubeSat way back when. He came to see us, in the mid-aughts, and he said, this is Bob Twiggs. Oh, it looks like you're having fun here. Can I come play with you? Bob Twiggs is a great guy. One of his quotes is, kids love 2 things, dinosaurs and space. And they're not making dinosaurs anymore. So he's a great blue sky guy, and we're glad to have him. So if you ever come to Moorehead, you might get a chance to meet Bob Twiggs. We regularly use the dish for things. There's Mikey up in the bucket truck where we do feed changes. I was involved in the design and development of the dish back in the year 2000 before I joined the staff there, and I specified it to be a prime focus dish. That way we could develop the feeds to go into it, because after all, it is the feed that personalizes the dish, right? Otherwise the dish is just a big mirror. And so putting that feed in there makes it do what you want it to do, and we can do everything in our labs. We have an anechoic chamber, a CNC machine shop, all this kind of stuff. But lately, we've been lucky enough to have enough money, other people have been building feeds for us. Some of the things that our astrophysics guys do, they're real big on AGN stuff. They really like that, galactic nuclei, supernova remnant, of course, galactic ray bursts. And then, of course, we always throw that in there. This is what I do. I'm not an observationalist. I'm an instrumentalist. I build this stuff, somebody else plays with it. And sometimes it's frustrating because I can build more than I can find people to play with this stuff for. And then, of course, an interesting thing that happened was we were given a pulsar system. And I'll tell you about that in a little while. So some of the things, once again, I like showing the pictures of the dish. This was lunar flashlight. We eventually did not participate in this program, but it was a light sail. It was going to be one of the satellites that moved, or it was going to use light to move it into position around the moon for its water search stuff. There's one of our boys down there. I'm the antenna guy, so when you see antenna blades sticking out of things, that's me. What else is cool on there? Oh, one of the things that we got involved with, well, two things. Well, three things. Planet Labs, the biggest CubeSat user on the planet. A really cool thing, we were in their first, or one of their first Earth stations. You probably never heard of Planet Labs, have you? You watch the evening news and you see pictures of the Earth. Look at the corner, it says Planet Labs. Planet Labs decided that they could put a constellation of 88 satellites up that would orbit the Earth, CubeSats. They would put a satellite over any point on the Earth within 15 minutes. So if you want to know what's going on somewhere, you could call them and get a picture taken. Well, their resolution isn't as good as the big boys. It's not like a spy satellite. But then again, you ain't going to get a spy satellite picture in 15 minutes, even if they would give it to you. It's expensive to move them around. So this way, you have this swarm of bees covering the Earth all the time, taking pictures. So a forest fire breaks out, if there's a flood, an army invades, a typhoon, tidal wave, whatever, you can get data pretty quick. So that's made them very popular, and they've made a lot of money, and I think Google bought them for $1 gazillion. And then we were involved in the Lunar Reconnaissance orbit. That was one of our first efforts in lunar water. That experiment was one where they impacted the moon. They detached the satellite and impacted the moon with it and created a debris cloud so they could do spectrographic analysis of it. That was kind of fun. And then this one, the ISEE-3. Anybody heard about that? This is one of the coolest things going. This was a satellite that was launched back in the 70s to do solar research. It was appropriated for a cometary mission in the 80s to go look at a comet. And the solar guy said, well, okay, we're going to let you take this and go look at the comet with it, but when are we going to get our satellite back? And the cometary people said, well, come back around in about 40 years. It's like, yeah, big help, 40 years later. 40 years later, it came back into the solar system. And we were involved in the reactivation of this thing, and we tried to steer it to an orbit. There was a whole group involved, and we were one of the participating Earth stations. It was a really cool mission, and it actually worked. The thing came back into the solar system, the solar panels were illuminated, the thing woke up. Nobody knew how to talk to it. We actually found the files in a guy's garage who was ex-JPL, who had the code on how to talk to this primitive. And how that happened was a guy was walking out of JPL, one of the people we were working with, Dennis Wingo, and he runs into this guy, and the guy says, here, I'll escort you to the door. Oh, okay, thanks. Well, you work at JPL? Yeah, what'd you do? Oh, I work on this thing, ISEE-3. Oh, really? I'm looking for the code on it. Oh, I got that in my garage. I took all the work. So you talk about serendipitous things. So they woke the thing up, we talked to it. It's my best DX. 40 million miles.
But I pressed the button on the transfer.
Yeah. So I can claim it because I was standing.
I detected it using one of those $20 SDRs.
So that was fun, but we were proud of that. But what happened was they attempted to steer it into a heliocentric orbit so they could recover it to do things with it. And one of the propellant tanks had developed, hit probably by a micrometeorite, and lost some pressurization, so they weren't able to get it exactly where they wanted. But I will make this comment. It is an example of the country that we used to be, and the engineering that we once did. That a 40-year-old spacecraft that has been in the harshest environment that one can even conceive, radiation effects, cold, heat, etc., could come back to life and be commanded after that period of time. We should all be very proud of that kind of thing. That really kind of moves me. So that was kind of a fun thing. And here's some of the other programs we've been involved with over the time. And then here's more stuff about the dish. It does move very fast. This was made for tracking LEOs. 6 degrees per second in AS and 1.6 in L. So this thing, you know, it's a quarter million pounds of iron, okay? Moving across the sky. It's kind of fun to watch.
So how much time horizon to horizon?
30 seconds,
Minute 20.
minute, something like that. Yeah.
It's a little slower going up.
Well, that's right,
Sometimes.
because it has acceleration profiles. So it doesn't go zoom. It starts up and it speeds up and then moves fast, and as it gets to where it's going, it slows down and creeps into where it wants to be.
It
So
moves
let me
fast
ask you
enough,
that.
you don't want anything to go wrong.
Well, there's that, and there's lots of safety features to prevent things like that.
So let me ask it a different way. What's the lowest LEO you can follow?
I can follow it down to the horizon.
1 degree.
No. What's the lowest elevation?
1 degree
Altitude. What's the lowest?
Oh, well, wait a
The
minute.
lowest of
We
the
can
low.
follow all of them, because the lowest LEOs that anybody's putting up are around 180 miles. They're kicked out of the space station. We track those regularly. In fact, we're tracking an experiment now called Asteria. And it's an experiment that was designed by JPL and MIT. We work with both of them very closely. And it's for discovering extrasolar planets. And it's been very successful. It's a CubeSat, has camera systems and stabilization systems on it, all this great stuff. It was thrown out of the space station, and it was going to last 3 months, and we're now, what, a year into it or something? 9 months? 9 months into it, and it's still going. So we've had renewals of that contract to continue the tracking of it. So that's kind of fun. Back in 2012, after we did the LRO, NASA said to us, gee, we kind of like working with you guys. I said, we really like working with you. And they said, well, what can we do for you? I said, well, we like this tracking stuff. They said, how would you like to join the Near Earth Network? So we said, okay. So they gave us 500 grand. That allowed us to do some instrumentation upgrades, and we got some interesting digitizers and things out of it. Here's all this stuff, you know, array-to-array, high-speed digitizer thing, some very specialized SDR stuff that's, what's the company? It's a T400. Oh, hell, I don't know. I'm getting old, I forget stuff. But anyway, we got some cool stuff out of it and really upgraded our capability, but it turned out the Near Earth Network never really used us. But it was okay, because one of the things that allowed us to do was we were able to implement the remote control regime and get the fiber optics all going so that we now could control it from down at the Space Science Center. All right? Instead of having to come up here to the lower equipment room and control it. And that's kind of tough to do in the wintertime, because we're on top of a ridge and there's ice and snow, so there were times when you didn't really want to go up and work on a dish. Now we have 365 availability of the dish.
What's a T400?
T400 is this it is a software-defined radio backend that's completely programmable, and it's made by a company called RT Logic. It just came to me. And it's in use by the Air Force and NASA and just about everybody for these kinds of missions, the very, very serious spacecraft missions. And then we'll talk a little bit about the JPL hardware.
Emergent front end.
Yeah, emergent front end, that's a different.
SDR.
No, the Emergent is this bought made by this company called Emergent is actually the interface between the T400 and the internet. So they call that a back end, but to me that's not a back end, that's a front end for the internet. And to me a back end is a thing you hook onto a receiver, so that's the kind of thing. So anyway, here's some more stuff. We've gotten involved in the interplanetary small sat arena. Here's a look in the lower equipment room where people used to sit, and here's a look in the current control center, mission operations center in the Space Science Building. We have a nice building, $17 million, 47,000 square feet, big star theater in there. We have a clean room, anechoic chamber, CNC machine shop, my RF lab, Bob's RF labs, a lot of storage because I have a lot of junk. Anybody who knows me knows that. And so, but it's because of all that junk we're able to do a lot of things. So here are some of the things, and some of these slides are a little dated, but they cover a lot of the stuff we've done. And then I'll move along. Anybody, by the way, if I go too fast, have me stop. I talk quick. I'll be happy to talk to anybody after this if they miss something. But we were invited by the Jet Propulsion Lab to join the Deep Space Network. Well, I tell people that and $6 will get you a cup of coffee at Starbucks. Because to most people, they wouldn't care a darn about that. But to us, that was a big deal, because there are only 3 DSN sites in the world. And they handle all the space probe radio traffic from Voyager, from everything that's going on. One of them is out in the Mojave Desert at Fort Irwin, Goldstone. One of them is in Madrid, Spain, and the third one is in Canberra, Australia. And the physical locations of those on the planet allow them to have basically 24/7 coverage of anything. Okay, cool, they already have sites. Cool, they've been in business 50 years. They really know their stuff. Why would they want us? Because they are fully scheduled. There is no slack time. They begin a year out, at least 6 months out, negotiating for who's going to get time on what dish, on what day, at what hour and minute. And if something happens, that's all renegotiated, it's done. I mean, it's like a continuous bunch of lawyer process thing, negotiating for this. And so now we're going to throw a bunch of CubeSats into the mix. Guess what? There's no more dishes for them. And so a lot of these early CubeSats, like the ones that are going to the moon, fall within our wheelhouse. We have a 21-meter dish. We can't see too far out there into space, but we can go to the moon. We can go out maybe 1 million kilometers very nicely, and we can go to Mars at a lower data rate. So we're not going to be talking to Voyager out at the edge of the solar system, but we can talk to things close in, and we can relieve the burden of these new spacecraft that are going out, because CubeSats have evolved from this stupid little 4-inch, 10-centimeter thing that you couldn't do much with into a real tool. About 2009, the government woke up and said, oh, now mind you, these things have been in business for about 10 years already. And everybody's just laughing. Space debris, these are useless. They're only good for training kids in colleges on them. About 2009, people around the world had begun to design real payloads to do real things. And they were shoehorning them into these little boxes, a 1U or a 2U or a 3U, and they were making them do stuff that it was like, wow. And I can get them up in a year or two, and they're only $1 million when you get it done. You don't have to wait 7 years and $400 million later to do something. Are they going to replace the big boys? Hell no, they can't. There's not enough stuff on them. But they're an excellent tool to augment. And they allow you to do things quickly. For example, the military is interested in them because you can put a constellation of them up and you can replenish them easily. Something happens to them, they die, you can launch a few more. Who cares? So, as a tool, they become a big deal, but to the DSN, they were a big problem. And then they got to talking to us, and they knew how crazy we were. And they said, you guys could probably support us in these missions. I said, we'd love to. Oh boy, we had no idea what we're getting into. What an adventure this has been. But you need a lot of stuff, and this key right here, no commercial off-the-shelf equipment exists. They have developed everything custom for JPL, for the DSN, because they have a very specific mission. It's very quality driven. They do not want to lose data. You got something that's, a gazillion miles out there, and it's transmitting, it's dying. You want to make sure you don't miss anything. So that is the overdriving factor for that. So we found there's no tracking, no telemetry, no uplink stuff you can just go by, no data collection. GPS isn't good enough for a time standard. Even a cesium and rubidium aren't good enough. So all the standard stuff aren't good. We had an existing X-band feed from the LRO project. That wasn't good enough. All of our processors, the T400, all that's not good enough. So this last one. So you're going to gather data for them. You're going to put it on the internet. You're going to ship it out to JPL, to their missions operations center. It's got to all be secure. People are very funny about their space probes. They don't want anybody else getting their data before they do. That's really it. Plus, there's the aspect of some other country might want to know what it is, and so the scientists who are running the space probe and own it, they want to get that data and analyze it and go through it and then release it to the public. So this last thing was actually a big thing. It was a tall tentpole. It was surprising. This is a NASA chart. It shows, here we are out here at Goldstone, and here we are at Madrid, and here we are at Canberra, and look at this little place in the middle of nowhere, Moorehead State University. We are actually DSS 17, Deep Space Station 17. We've been assigned a real number, we're part of the real thing there. This is a big dude in NASA, if you look him up. In fact, it's been said that one day he may be director. I know him. He's been out to see us. He's a hell of a nice guy. Of course, that's my boss. And this guy, Jay, he's marvelous. He has been a big help, and Tim Pham, the guy who's the Chief Communications Engineer for the DSN. So a little bit more of this, I'll zip through it. It was decided that we don't need the full up capability of everything they can do, because they have a Ka-band function, they have an S-band function, an X-band function, so they have a lot of complexity built into their system to cover different bands. We were only going to do X-band, we were only going to do things at a certain data rate, we were only going to do things at a certain power level. So we basically sat down and stripped down their block diagram and figured out what we needed to do, and came up with a much reduced block diagram for things. I already alluded to this. Getting stuff out onto the internet, well, they have actually a secure internet that we go through. So we're on the NASA, what do they call that thing, Bob? The IONet. We're on the NASA IONet, and NASA CSO is their communication services offices. They built a whole rack of equipment for us. And they brought it out, and the guys came and installed it and hooked it to the fiber, and that was just the beginning, because now they start doing security pinging. They're coming through their firewalls, and they're looking at all our hardware, all our computer junk out there, telling, oh, this thing's no good, you got a leak here, you got to fix this, oh, this thing's no good, you got to take this software package out of that. So it's been very, very interesting. There's another view of the Missions Operations Center that we have at Moorehead, and there's the dish on the hill. This portion of the building is cantilevered out, so that when you're sitting in there, you can easily look up and watch that dish. You know why? When you're moving a $3.5 million thing that weighs 250,000 pounds, you want to make sure it's doing what you want it to. You don't want any surprises. So we have visual verification of what's going on there. Oh, I went back too far. Where's my back? There we are. So this is a rehash of a lot of the things we've ever discussed, but here's some of the current status of things, and we'll talk about these things a little bit more quickly as we go along. How am I doing for time? Okay, I got a little bit of time. Here was one of the tall tent poles. By the way, this is a view of the lower equipment room and some of the stuff we had in there. This is the first radio astronomy system that I built for Ben back in the 90s. It's still in use. This synthesizer and some of this power distribution and all this stuff in there. This was the cesium beam we had back in the old days. But none of that was good. We had to get a hydrogen maser because we needed a specific stability requirement within a specific time regime. In a time regime of 1 to 100 seconds, we wanted this thing to be accurate or stable to within 3 parts in 10 to the minus 13. So that's pretty good. You can't get that with any other standard. That happens to be the sweet spot for a hydrogen maser at $500,000. Where are you going to get that? We didn't have $500,000, but we had friends. So some guys at NASA said, well, you know, we got some in storage for some tracking systems, and they could probably be brought back to life and everything, so it's great. We're going to get one. Then they come back and say, no, we asked Joe, and he said, you can't really have that one. He's got plans for it. Bill wants the other one, so you're out of luck. So our friends up at Haystack Observatory at MIT said, you know, we've got one here we kind of pushed into the corner, and we've got a newer one. This one needs refurbished. It's got a few things you got to do to it. We said, hey, no problem. So we sent a student, Cadence Payne, really nice gal. She went up there and she worked for a summer, and she worked with the people up at MIT, and she learned about the maser and learned about what was going on and the rehabilitation of it and everything, and then we transported it down. It was basically free on semi-permanent loan, and we had to pay for the hydrogen bottle and something. Because you know what happens in a maser is it runs out of hydrogen. Well, that's no big deal. You put another hydrogen bottle on it, except you had to put a new fittings and things.
They kept it energized when they moved it.
When they moved it, we had battery packs and inverters and everything in the truck, and it was all strapped down, and it came down hot. And it came and was installed. This is the glow of the hydrogen maser. We have a little camera set up in there, you know, a Raspberry Pi, looking down there, and we got a screen in the control room so you can see the maser lit up. That's what the maser looks like. That's the big jug in there for it. They liked Cadence Payne so well, they offered her a free ride to MIT for a PhD program. These are the opportunities our students are getting. We're in Kentucky, 4 million people, half of the amount that's in New York City. And yet we have 5 interns at JPL this summer. We have kids that have gone to NASA up at Glenn, NASA at Marshall, all over the place. And we have 100% placement for our students. Nobody goes without a job when they get out of our program. And now we're getting more and more exposure. It's accelerating faster and faster. I'm really happy. You know, kids will come in and they'll, hey, how you doing? They go, oh, another day building satellites. They say, you know, I I would have killed people and crawled over the bodies for the opportunity to get in the lab to build satellites. And they're like, no, they build satellites, putting solar cells on. These solar cells are $400 a piece and they snap like potato chips. And they're in there mounting them and bonding them down and all this. So they're learning real stuff. So it's a lot of fun. You know, once again, a look at this guy, our dish. This is one of my inventions. This is the co-resident UHF feed array that allows us to do 400 to 470 megahertz with the prime focus in place. So that I always have a UHF capability as well as whatever else is in there, S-band, X-band. I look at one of Bob's SDRs running. This is the experiment package for LRO that we actually taught for the satellite orbiting the moon. Quick little story about it. So you think you know where your dish is, and you think you know where it's pointing, but you don't really. And so APL, Applied Physics Lab at the Johns Hopkins University, was working with the LRO. They're working with the mini RF experiment, which is a phased array radar looking at the moon. And this phased array radar looks at dual polarization because that's how you find ice. There's the world's expert on space-based radar, Keith Rainey's up there, and I had the privilege of meeting this guy and chatting with him and learning a few things from him. And I learned about this cross-polarization ratio issue thing, where you can send the vertical signal down, and you look at the vertical coming back, you look at the horizontal coming back, and by looking at the ratio of these two things, you can figure out what it is you're looking at. Rock looks different than ice, looks different than lunar dust. And so this was pretty cool. And so this was all mechanized to do this. And so we worked with calibrating their radar system. We worked with communications with the satellite. We actually had 3 programs with them, 3 contracts doing stuff on LRO. There's some other pictures. So there's our new cryo LNA. Of course, you saw those racks. There's the Mission Operations Center. There I am sitting in the background. And of course, there's a view of the dish. You're going to get tired of seeing the same dish pictures, but we like it. This is the picture that shows the sites. This is 70 meter out of Goldstone. There's Moorehead. There's Madrid. It has a 70 meter there. And there's Canberra on the end. The dishes, I've been out to Goldstone and I got the Cook's tour. I got to go climb on stuff and go into places and around corners, and it was a blast. And their dishes are super special. Their dishes, in fact, I didn't throw any pictures in on this because I'm going to run out of time anyway, but I'm doing my best. Their dishes are called beam waveguide dishes. They're 34 meter dishes. They have a subreflector at the focal point. They got a hole in the middle of them, and they have basically what you would consider a microwave optical waveguide system, and huge overmoded circular waveguide that goes all the way down through the dish and comes out in the room underneath the dish. So they take all of the spectrum, all frequencies, and they pipe it down underground. And then they can put whatever receiver underground. What a luxury. Your gear's out of the weather, you can walk up to it and work on it. And at DSS 13, they have at the bottom a scientific Atlanta pedestal with a subreflector there, and it rotates. And around the periphery of the room, they have different experiments set up. So they'll have a 5 gig receiver and a 35 gig receiver and an L-band thing and something weird they're working on here. And they can just steer the beam to whatever thing they want. In fact, they have dichroic mirrors there that pass certain frequencies through them and reflect other ones down so they can run 2 simultaneous experiments at once. Really cool. And I mean, at $32 million, hey, by 2, they're small. But we'd love to have it. We'd love to have one. I'm truly envious of that because my stuff is out in the weather. A guy's got to get in a bucket truck and go up there and haul it down so we can work on everything. They can like sip coffee and play with their stuff right there. The next steps we had to go through. Here are some of the milestones, and we've met most of those along the way. Oh, there's that picture of me in the background again, but you get a different view of the Mission Operations Center and some of the stuff. Ben sort of created it to look like a NASA mission control center. So we got the big screen TVs up there so you can watch stuff. When we launched Kentucky Sat-1 from Vandenberg Air Force Base on the Glory mission. It went off at like 2:15 PST, and we're there at 5:15 EST in the morning. We had the president of the college and the provost and everybody in there. The mission center is packed because it's one of our first missions to go up, right? If you know anything about the Glory mission, it was a $400 million satellite that NASA had worked on for years, like maybe 8 years. It was finally going. It was a big deal, an exploration satellite. And the 3rd stage shroud did not separate, so the whole thing went into the drink, carrying our little CubeSat with it. Well, there were some mighty long faces in the room, I'll tell you, when you looked around all those students who had worked for a year and a half on building this thing. And I said, hey, guys, it is rocket science. You know, once you hand it off to NASA and they accept it as being ready to go, you're done. You've won. It's in God's hands from there, because anything can happen on the launch pad. And that tended to lighten the mood a little bit, you know, but I imagine the NASA glory guys, now they were probably a little sad, because that was big money for them to lose into the Pacific Ocean. There's the SLS-1. It's got an adapter ring at the top. In that adapter ring, there's a slot to hold 13 CubeSats. NASA grabbed the first 3 slots. Then they put out a call for proposals for the remaining 10 slots that were in there. We were the next one chosen. We're number 4 in the adapter ring. They liked our mission a lot. So we got the next slot in there. And there are various other organizations, Arizona State, lots of other people are in there as well, but we're kind of proud of that. So when it leaves the Earth, it's very interesting on how our satellite is going to get to the moon. One of the people at Goddard is really big on this low energy manifold trajectory maneuver system, where you launch something, you maybe get out to about the Van Allen belts, you cut it loose, and then it goes out, loops around the moon and comes back, and it looks like a bowl of spaghetti by the time you trace out all the paths of the satellite. And the purpose of it is, it loses enough delta V to finally enter lunar capture. Because otherwise, you're just going to fly past the moon, and the moon's gravity is not strong enough to grab you. So you have to lose a lot of velocity in the process. It's going to take us 270 days to go to the moon, because of this process of looping around, going back and forth and everything. And so our satellite has to exist in essentially deep space, because once you get out past the Earth's magnetosheath, you're out where the radiation effects are intense. So we've entered the realm of the big boys now. When you're doing a CubeSat and you're shielded by the Van Allen belts, you can get away with a lot of stuff, but we don't have that privilege. Our stuff is going to get hammered on by particles. So it's got to last 270 days, and it's got about 6 months of actual mission. We'll be happy if we get a month out of it, okay, by that time. But anyway, some of the looks at that, that's a pretty exciting thing coming up. You can watch for it. Here's something that's interesting. Because the DSN is so tightly scheduled, people can't do experiments on it. So they come up with really interesting things they want to do, but, you know, they'd have to bump somebody. So here's a couple ideas that have evolved. They want to do this opportunistic multiple spacecraft per aperture. What that means is, because there's going to be so many spacecraft around the moon, and they're going to have to service each one individually to talk to it, they're coming up with the concept of, you know what, while we're talking to Joe here, we're just going to have Bill and Susie and John over here transmit their data down at the same time, because they're all on different frequencies. So they'll just be sending their stuff down while we're servicing one satellite, and we can capture their data as well. So we performed the first ever experiment of that done in the DSN at Moorehead on a mission that I'm going to tell you about shortly that went up in May. And so that was a proof of principle thing, and they were very happy. Another thing that we're working on is delay-tolerant networking. Now this is a big thing for outer space. And it's really kind of packet communications that we do with packet systems. Normally, you know, they send a packet of data to you. Did I get it? Yeah, I got it, or I didn't get it. You know, resend it. Well, that's a lengthy process. And so in this way, in the case where there will be multiple spacecraft or multiple assets involved in the hop, I'm going to cut this story real short, you can store the data at the last position. And so you can say, hey, I didn't get it. And you're just going back one level. You're not going all the way back to the originating point. You're going back partially along. Well, you know, this makes perfect sense to you, right? I've never done this before. So there's a whole crew out there that are doing this. And I'm trying to remember what the remember your guy's name?
Nate.
No, that's our guy, Nate Richards. Nate Richards, did he get picked up by aerospace?
He did. No, he got,
Oh, he went to JPL. Nate Richards, one of our grad students, just got offered to go to Aerospace Corporation. He turned that down to go to JPL. So kind of fun.
same pay.
Same pay. A little more aggressive. So you want to be a DSN station. What's needed and why do you care? Well, all right, precision frequency we talked about, a master clock assembly, which is a weird thing that's built specifically for JPL. You need this 100 megahertz maser. You have to be able to calibrate your system and precisely measure the time delay from your transmitter all the way up through your feed and back down to your receiving and demodulation system. Why? Because they're able to navigate spacecraft out at Jupiter to within 10 centimeters. That's not very much error. And you can have more than 10 centimeters error through your system. And so we have to come up with this precise calibration routine. We're going to calibrate our system and take out all the errors from it. We have to have all sorts of monitoring in our system and archival methods so that, because they don't care. They don't want this until there's a problem with the mission. And then they want to go back and do a post-mortem. Why didn't we get that data? Was it the spacecraft? Was it the tracking station? What happened? So we have to implement exactly the same regime. We are going to be transparent to the DSN. In fact, to the extent that we will not schedule ourselves. We are scheduling time for ourselves for our Lunar Ice Cube mission through the JPL Missions Operations Center at the DSN. We've made this decision that we will behave exactly like every other station around the world, and that they will schedule us, and that we'll request time for our own missions through them, and that way it makes it easy for them. They don't. If we did it ourselves, they'd always be saying, "Are you guys available? Can we use you? What can we put you in?" And then they wouldn't want to use us. So we made the decision to just totally submerge ourselves in this. But in order to do this, we have to be form, fit, function compatible. We have to be absolutely transparent to the user. So we have to look as much like a real DSN station as possible. So you need low noise amplifier, you need a high power transmitter, you got to have a good feed system and a good dish. Well, we have that, and I probably forgot some things, so we'll just move along with that. Frequency and time standard system. We use GPS to get IRIG, Inter-Range Instrumentation Group Type B, into this, to the master clock. This guy provides the frequency standard to that, and then using an optical link, it's distributed among the racks. So they have a very, very specialized distribution system to get time and frequency into all their stuff, and they only care about down to the second. Deep space missions are second increments. Of course, a light second, half of a light second is 90,000 miles. So they have to know where the spacecraft is within a half of a light second in order to do this. This was my contribution. I designed this feed system. It's completely polarization diverse. It's right-hand, left-hand circular. I can transmit and receive copolar or cross-polar. I can switch anything around I want. I have my very fancy LNA in here. I have a block-down converter in there. A test translator allows me to do the calibrations, and all this fits into a drum. I'll show you.
Yeah, but your controller's real expensive.
Yeah. Do I have it on there?
Yeah.
Yeah, the rent's high. In fact, I began as a student project, and that was one of the senior thesis projects. I gave it to a guy, said, write some software to control this stuff. I designed an interface board and built it, all surface mount, because we have surface mount capability. And gave it to this guy, and he worked on it for 8 months. Didn't get too far. Typical senior, got a guy to cut in. He's at the Craft Academy, which is one of these things where you can, as a junior in high school, you can go to college. They pick the best of the best among the high school. We have that at Moorehead. They get 60 kids a year coming in each class. This kid walks in, and I know him. He'd been to visit me before. And he just loves stuff. I mean, I wish I had 100 of them. He came in, and I said, hey, Jeremiah, you think you could do me a command line entry for this? That was Thursday afternoon. Monday morning, he came in and had it all. The senior kid's sitting there going, Jeremiah, the 11th grader, he's sitting there explaining everything about Python, Java, and how to do these libraries and interlink things and blah, blah, blah. And I'm like, this is great. So I hired him. He's working there this summer. He's actually in my lab right now doing stuff, and I'm going to mentor him all through college because this kid is special. But yeah, so here's some of the things that are inside the feed. Here's one of the things I also did. This is the byte system. It has a power meter, so I can sense the transmit power. I've got 3 kilowatts running this way, up to 3 kilowatts. I pull off minus 50 dB down, split it. I can look at it on a power meter. I can run it through this test translator and translate from the transmit band to the receive band. It's very interesting how they do their conversion schemes. It turns out that this is 100 megahertz wide and that's 90 megahertz wide. How do you map it? Well, you map it using what's called the turnaround ratio. The turnaround ratio is how deep space probes can figure out what frequency they're on. The frequency that they transmit from space is based on the frequency they transmit from Earth. And they use a precise ratio to send it back around. That way they don't have to worry about the clock on board the spacecraft drifting. And that ratio is 880 over 749, which is the DSN standard. And if you take that and divide it out, it's a little bit greater than 1, so it takes 90 megahertz and maps it to 100 megahertz. And so this signal comes from our DSN furnished equipment. But there's something I'll comment on in here. I built that all out of stuff I had laying around, because I have thousands and thousands of microwave parts in my inventory. I literally do. It took 15 tractor trailer loads to move me from Baltimore to Moorehead. No kidding, a year and a half. But I didn't use my old phase lock oscillators, the one I bought brand new ones.
Yeah.
Because the brand new ones are so much better. I said, so they charged me 30 grand for 6-phase locked oscillators, right?
Who'd you buy them from?
Mytech. And, which is a very good company. They make very excellent equipment. I'm sure there are competitors that now make things almost as good as Mytech and probably a lot less money. But I went to Mytech for these things. They're coaxial resonator oscillators, miniature things, little tiny things. And it took like a year to get the damn things, and we finally get them in, and I'm there like, okay, I spent 30 grand on these. How do I know they're really any good? How do I measure their phase noise? So the JPL guy's sitting there, and I say, hey, Tim, you got a phase noise measurement capability on JPL? He goes, yeah. I said, would you measure these for you? Oh, okay. So I put them in a box, shipped them out to JPL, had them measure them in their lab, and send them back, and you know what they said? We couldn't measure the phase noise. It was better than our system. They said, where did you get those? I tried to buy the ones JPL used in their systems, the part numbers, right from Mytech. You know what Mytech said? Oh, we don't make those anymore. But we'll make you something new, and we'll charge you a pile of NRE to do it. And I said, oh, okay. So that's what we did, and it turned out to be a good decision. Here's a little bit on how we distribute signals. Everything comes up on analog fiber that we want. We send the 100 megahertz reference up. We bring the receive IF back, and the transmit IF goes up. But I'm going to take this turnaround ratio IF, and I'm going to frequency multiplex it onto the fiber to save one fiber link, because I don't use that all the time. It's rarely used, and so I can do this. So a real simple little filter arrangement to get it onto one fiber and strip it off again at the top. Here's what the feed looks like inside. So I made sketches and sent them off to this guy, Jeff Hazelwood, at this company, Memco. He came from where Bob did, Comsat Corporation. He builds some of the finest feeds going. He builds feeds for everybody. Lockheed Martin, name them. I mean, Mytech, he builds it for Florida, L3, DirecTV, all this stuff. So I sent my sketches up of what I needed, and this is his sketch of the waveguide tree, the orthomode transducer, and polarizer assembly with the feed horn on the front. That's a scalar ring on there. And here's what it looks like in the experiment container. Okay? When I first came here back in the 90s, I saw the feed canisters they used on the 140-footer sitting over in the basement of the Jansky lab. And I said, yeah, that's a nice way of doing things. If we ever build our own dish, we'll do the same thing. And we did. So we designed this, and Vertex manufactured it, so we have these feed canisters we can lift in and out. You'll see us doing that here in a minute if I still have enough time. I have 10 minutes, I gotta run. Here's the baby, $100,000, cryogenic LNA. I would have never thought we'd have one of these in the world. If we don't have this, nothing works. You gotta have this, 17 Kelvin at X-band. What's wrong with cryogenic LNAs? They got some kind of cryogenic stuff in it.
They don't work.
No, they work great. This thing works like gangbusters. And let me tell you more about it. Not only does it work, but it's maintenance free for 10 years, guaranteed. You don't have to touch the compressor. The compressor's right here. The LNA's right here. The whole thing's as big as a bread box. Now this is the technology I'm sharing with you today. So you say, why is this good for radio astronomy? I don't know. Maybe in 10 years you'll be walking through a ham fest and you'll see one of these things under a table for $20. Buy it! The point is, that maintenance-free aspect is amazing. So the guy, Steve Rawson, from the company Callisto, which is located in France, he's an Englishman, but his wife likes French food. They moved to France. He worked for the European Space Agency designing cryogenic amplifier systems. He flew over to see us. This is the first one that's been sold in the United States. DSN had never seen one. NRAO had never seen one. No idea about these things, right? Well, it's actually not cold enough for some people, 17 Kelvin. I mean, that's pretty hot, right? Because when you go out to the DSN, I'm walking around in there and I'm looking, and you know, I see Omega makes temperature indicators. I see this Omega temperature readout. It says 4.2. And I walk over and look at it. It's 4.2 Kelvin. That's liquid helium. I said, 4.2. Oh yeah, that's what all our masers run at. All their stuff for DSN are masers. I've never even held a maser in my hand, and I have an enormous amount of junk. I said, I've seen measures in a book, but I've never held one. He goes, oh, well, the guy who built them all is over here. And he calls them over, and I meet the guy who's built and tuned all these measures. And we get to talk. They're 8 Kelvin. Now, you know, you're not going to get a whole hell of a lot colder than that, guys. So this is about as low a noise of technology as you can reasonably expect to achieve. And the beauty of this is, so I'm talking to this guy, Steve Ross, and there he's in Ben's office, and I said, man, I'm really impressed with your system. 10-year guaranteed lifetime. And he goes, oh yeah. And if the compressor fails, 4 screws, you pull it out, stick another one in. And I went, oh, you didn't invent that. Because you guys know what I'm like. I said, you didn't invent that. Where'd you steal that from? He goes, oh, MRI machines. So in an MRI machine, there's a compressor. It'll take you down to 77 Kelvin, and then it pops in and out. How about that? So then I said to the guy, this little face saving for him, well, what was your secret sauce? You must have done something. He goes, oh, aerogel. If you know what aerogel is, it's this almost invisible, almost weightless substance that doesn't conduct heat. He filled up the entire vacuum vessel inside with aerogel, so there was less vacuum vessel, and even if the vacuum failed in there, the aerogel still helps protect from heat conduction from the outside world into the cryo area inside the air. So it's really cool. The trouble is, it's got a big controller that goes with it and 3 huge cables to hook it up. Now, if you're running this 200 foot up into a dish through a cable wrap and out through joints and elevation knuckles and things, that's a pain. So Bob is credited with coming up with a solution for that. We'll get to that. But there it is, serial number 1. This is 20 Kelvin. This is their typical temperature curve across the 8 to 8.5 gigahertz region. So if you look at that 8.4 to 8.5, it's relatively flat, and it looks about 17 Kelvin. And there's multiple traces on there because a statistical sample of 1 is invalid. So they measured it several times to say, yes, this is really true. And there's the spec sheet above it, and here we are. This was the controller. Holy cow, it's nice. It actually has a fairly powerful, I think a 4-core Pentium in there.
Yeah.
They use in traffic light cameras. That's where they got that.
Computer runs Windows.
Whole computer. It's a Windows computer in here, and then some of their special interface stuff was here, and then just some power supplies. And we're like, yeah, this is a bit of a pain. How are we going to deal with
See
this?
all the cable in the back.
Yeah, there's the roll. There's some of the cable. A roll of some of the cable to get up there, right? So that's trouble threading cable up through all these cable wraps. Here's a little plug here. You know, because I'm such a junk man, I have so much stuff laying around. And when we talked to JPL about what we absolutely needed to buy for the RF stuff, they said, well, you need these boxes that are made by JPL, that's 125K. And you need this stuff that we buy from Mytech, and that's about 450K. I said, Mytech? They said, yeah. I said, well, you know, I got a lot of that stuff in the back room, maybe I could build that. So, of that 50K, 30 of that was oscillators. I went in the back room and I pulled out this stuff and pulled it apart and retuned filters and recalibrated stuff, and I built all the DSN hardware out of my junk pile. How about that? Also, my boss liked that too, let me assure you. We built a complete duplicate set of this and put it in the control room so that we could calibrate the stuff in the control room. A lot of the stuff that I built had to go up into the feed, but we have a duplicate set in the control room, so we have a very unique opportunity. We can calibrate other people's spacecraft. JPL does that. The Iris radio is an X-band radio. It only costs $1.5 million for a 2-watt transmitter to go to outer space.
It's radiation.
Want to go to space? Just add money. So here they are. People get this radio, they integrate it into their spacecraft. Now it has to go out to JPL and be qualified for EMI and all this other stuff. And they do this at what they call DTF-21, which is a test facility. $45,000. We actually built the same test facility because we have JPL back-end equipment and my front-end equipment. We built that in our control room so we could go right up there and calibrate our own stuff. And because they're qualifying us, they can't argue with our results. Here's an example of the block-down converter system that I built. There's one of those expensive little phase-locked oscillators. Of course, you know, isolators, circulators, mixers, a retuned filter. I taught one of my students how to tune filters. He loves it. He says, you got any more? I said, sure, here, retune these. He sits in front of the network analyzer, twisting screws, trying to get the shape of the filter to look just right, you know. So he has a real good time with it. But this is where I did not chintz. I did not chintz here on buying those oscillators because those are really the cat's meow. So you spend $100K on an LNA, how do you know it works, right? You can't test it on a machine like Charles. They're wonderful machines, but at that level of precision, the measurement uncertainty is more than what you're trying to measure. So you can't use an HP noise figure meter or anything like that. You have to go to a Y factor measurement where you use a hot-cold noise source. So we wanted to verify that the amp was really kind of doing what they said it did, at least to some level. And so Bob comes to the rescue again because he had done this on Earth stations around the world. He had the equipment, the software, and the expertise. So you talk. It's your turn. I'll take a break.
So I've characterized several LNAs, probably 50 or so, different bands, KU band, C band. And we use these gain plates in a spectrum analyzer and a power meter. So you can see there's a couple of the attenuators, and then there's a very nice little amplifier that has a high intercept point. And we run that into a spectrum analyzer, and then ultimately from the IF and the spectrum analyzer into a power meter. So using the software that I helped write at ComStat, which measures the Y factor, he looks at the power meter and measures when you flip the switch. So we have the waveguide horn looking up at the sky for a cold load because we didn't have a cryogenic load. And then we have an ambient temperature load. And we can then measure the Y factor. Now we checked this on a known LNA first to make sure that that concept would work. And then we took it up to the roof to do those measurements. Here's the confirmation from the known. And then we took it up to the roof and did it up there. And it was a nice clear day. And here I am pressing the buttons. You can see all that cable in this big old box, and we would have had to fish all this cable from down in the LER, the lower equipment room, up into the feed. We looked at it and said, you know, that's crazy. You know, something happens to this wire, you know, and there's not much in this wire, it's just some power supplies in the computer. So we used this, we powered it up. You see the horn facing straight up. I had the spectrum analyzer, the gain plate on top. One of the more difficult things with the spectrum analyzer is the log amp. And if you're not careful, you just saturate it. So the gain plate sets the level of noise. So when you amplify noise, you amplify it in a linear fashion. It's very difficult to amplify noise because it'll saturate your amplifiers very quickly, especially broadband noise. So one of the things we use spectrum analyzer for is we have a 3 megahertz filter, so we can do across the band and do the noise at different frequencies to get a nice profile of what it looks like over the band.
What do you use between the horn antenna, to switch between the horn antenna and the hot mode?
Baseball switch. It's a waveguide switch. Go back one, I think. We go back a little bit here. And this thing here, you're not seeing it, but on the other side of it, there's a knob. This is actually an electromechanical switch, but it has a mechanical actuator. And we can flip it back.
So it just moves a piece of waveguide and
Well,
lines it
yeah,
up?
if you ever look inside of a baseball switch, it's got these curved sections. That's what kind of looks like the stitching on a baseball. That's why they call it that. And when you rotate the knob, it changes the paths inside. So these are very, very common in equipment. Les has probably seen 1 million of them over his career. And
I've got half of what you've got.
there you go. And so you actually can fully automate Bob's measurement system by putting an electromechanical, using the electromechanical switch portion of this, but we did it manually because we're only doing it once and we just want to do verification.
Or we tie a string to it and just pull the string.
Because that switch has to be virtual.
That's if it's high up in the air, you can on the waveguide pull it straight.
This is not a dicky switch. This takes a significant
It
amount of
goes
time.
clap.
Yeah. Oh yeah, it's not an electronic switch. It's not instantaneous kind, like microsecond. It's whack. So we burned one out in the lab for $1,500. Gave it to the software guy who was working on that controller, the Raspberry Pi controller, right? And for some reason they had the thing in a loop, so it was going switching. But it didn't last very long. That thing got hot as hell and burnt it up. It's like,
So
back
what
to
is the
factory.
loss through that switch of EM? It must be very
Zero.
small.
It's
I mean, you
waveguide.
can
It's
virtually-
0.01 dB. I mean, it's way
So it's
up.
virtually just a piece of waveguide.
Yeah.
that-
In fact, it's a
Right.
very short piece of waveguide, and it's high power, and it's engineered for exceptionally low loss and repeatability.
Yeah.
So this is what the result was.
Hey guys, time.
We're getting, I know, we're getting up to the time. Can you guys give us a couple more minutes before lunch? We'll try to wrap it up at 5. But you'll notice here, 15 Kelvin, 16 Kelvin, 17 Kelvin. So our plot doesn't match theirs exactly over the 8.4 to 8.5. You know why? Because we don't really know the temperature of the sky. So if you're off by a degree from your sky temperature, you're going to be off by a degree in your LNA measurement. So
I
we were
find
close.
it hard to believe you couldn't get a cryogenic expand load.
Oh, you can. Just add money. We didn't have it.
Yeah, see where we came from back in the day, we had big tanks of liquid nitrogen.
And
We could
everything.
Go out there and tap off the hose and put it into a door. But we didn't
Yeah,
have
you know
that.
the hell
All
out
right.
of me when you did it.
Let me whip through this now. This is the mission that we just did on the 5th of May. This is Mars Cube 1. It was a historic mission launched from Earth from Vandenberg Air Force Base. 3 space satellites went out, 3 space probes, the InSight probe and the 2 Mars cubes. The InSight probe will detach a section of it that'll go down and land on the surface of Mars, and it'll be in a fixed position standing off of Mars, and the cubes will orbit Mars and act as data relay systems to relay the information from the surface site up to the InSight spacecraft, which then has a high-power transmitter and will link it back to Earth. And so this is what we participated in. And this is sort of what it looks like. They launched it from Earth, you know, the satellites come out from the shroud and deploy, and then the antennas come out. There's InSight, and here's the 2 Marco satellites. And then you see, here's on Mars, you get a landing on Mars, and the Marcos fly by and do their things. I think they're going to try for orbital capture. This was a historic thing for NASA, so this is a NASA slide from JPL, and here's some of the information about what it does, when they're going to do it. And then here is the tracking of the system. If you'll notice right here, here are the different stations. You know, we're talking Canberra and Goldstone and Madrid, and there's Moorehead. And this is an official NASA slide. And so you can see the windows for tracking it. The big boys are huge. And then you look down here and you see these little lines. These are the Moorehead tracks. So it's obvious we're not as capable as they are, but we're still in the game, okay? And so the proof of the pudding's in the eating. When they launched it, there was a frantic scramble for us to get everything together, and we had to actually interrupt the exoplanet mission to do that. And then we're waiting on the day of the launch. And we got everything ready for it. In fact, this is what Bob did. He repackaged that entire controller, eliminating those 3 cables, and he got it into the feed. So he took everything out of that rack box, got rid of those 3 big rolls of cable, and it's all in the feed. Here's our feed with all of our waveguide stuff and some lashed together systems. Here we're changing the feed out. This is how we do it. Bucket truck, there's a winch on top of the dish. We're lifting the feed up in there to put it into place. There's Mikey up there in the bucket truck. You see he's got the feed lifted up, and then he rolls it into place there. And then it gets lashed into all the stuff up there. This is my UHF thing. There's another view of it that I showed you. Here's the X-band feed in place. And then these guys are disposed off to the sides of that, so they don't block the view of the feed. There's our Mission Ops Center with all of our stuff. I'll just mention one thing. We were given a Pulsar detection system that's been at Arecibo in the VLA. A really nice guy by the name of Dr. Tim Hankins, whose whole life has been pulsars. He was a PhD student when Jocelyn Bell made her discovery. He switched his PhD dissertation to pulsars, became a pulsar guy. He built this system and he used it, and one of our astrophysicists was out at the VLA doing some work out there, and he met this guy and they're talking, and he, oh, what'd you do, oh, pulsars and all and everything. Our guy says, oh, that's real interesting, we're trying to do pulsar work, and this guy says, oh, you know, I got a whole pulsar system sitting in my garage, I'll debate whether to take the dump or not. And Tom says, we'll take it. And then so I got on, but let's call up and see if they want it. And I said, hell yeah, come on out here. We'll even pay you to fly out here and show us how to run it. So he and his grad student, who's now a PhD and actually teaching at a university in South Carolina, came out and showed us how to run all that stuff. So we got a free pulsar timer. I got to see Vela on it. We hooked it up just real quick, and I got to see Vela pulses and everything. He knows everything about pulsars. I know nothing. Here are our operators on the day of the Marco mission, all standing around, sitting around the control center. And here is the opportunistic multiple spacecraft per aperture thing. So there's 4 B200 Edis receivers here running new radio with 4 computers, and all of this is on the internet, so the guys at JPL were running it. So we're taking the IF out of our DSN stuff, running it into a power splitter, driving all those, and I've piggybacked the spectrum analyzer, so I'm looking at the spectrum of the Marco birds as they're doing their thing. And there's one of those generators Skip you worked on right there. Here's a shot of our DSN racks and the mazer beside them in the back room where we don't just let anybody in. This is all JPL furnished hardware. Well, a little bit of my junk's in there now. But it basically came from them. And here are the spectra from Marco. This is the, there's Marco B, here's Marco A, here is the InSight spacecraft communicating, and that's a blow-up of what their spectrum looked like on the InSight spacecraft. We got the signal exactly at the same time as Goldstone. Well, that's a big deal, guys, because that means our stuff all worked. And that we were all time synchronized and everything. So when that result came in, it was like high five time, and I told the boss, okay, I'm done for the summer. Take a little time off to do some other things. So hooray, it all worked. A historic mission. And this thing, we achieved everything we wanted to. Except we were supposed to talk to it with the UHF transmitter system. But they spent a lot of time making sure their stuff was all just right. And so they came to me and they called me one evening and they said, okay, we want to try the UHF uplink command experiment tomorrow. I said, tomorrow. I said, where's the spacecraft right now? They said, it's 850,000 kilometers away. It's out past the moon, by double. Where will it be tomorrow morning? 1,000,000 kilometers. I pulled up my spreadsheet, did it. I said, sorry guys, we ain't going to talk to it at 1,000,000 kilometers. We kind of missed the window. But that wasn't my fault. But here's the thing, that thing was really flying. Within a day and a half, it was past the moon. So it's going to get to Mars in a couple months. So it's really moving. And I know we don't have any time, but you could call me anywhere you want to and ask me questions. I guess we could probably take a real brief one now if there was something.
Where's the slide bank? Can we get a copy of the slides?
I'm sorry?
Can we get a copy of the slides of the presentation?
You gonna
Oh,
post this
sure.
on that?
Just email me.
Okay.
And I'll put my email on the board here if anybody wants it.
Thank you.